Today we are going to discuss about a basic concept, work. When a system starts interacting with the surroundings, the energy transfer occurs in the form of heat or work. When a system starts interacting with the surroundings, energy transfer occurs in the form of heat or work effects. So for a better understanding, it is essential to distinguish between work and heat interactions. So today we are going to discuss the work done by a system during reversible expansion or PdV work. Work done by a system during reversible expansion. Work done by a force is defined as the product of the force and displacement in the direction of applied force and the displacement in the direction of applied force. So mathematically, we can state it as dW is equal to F dz. Newton meter or joule. Where dW is the differential amount of work done and F is the applied force and dz is differential displacement in the direction of applied force. So work done by a system is the product can be defined as the product of force and the displacement in the direction of applied force, or it can also be defined as the energy expended in the form of work when the force acts through a distance. Energy expended in the form of work when the force acts through a distance. So consider a gas confined in a piston cylinder assembly. Consider a gas confined in a piston cylinder assembly. Suppose a gas is confined in a piston cylinder assembly. Piston. So we are going to discuss about the mechanical work transfer or the displacement or the PdV work. Displacement work or the PdV work which is associated with displacement or PdV work which is associated with closed systems. Mechanical work transfer between a system and surroundings, or it can be displacement or PdV work which is associated with closed system. We assume a closed system as a gas confined in a piston cylinder assembly. Suppose the system is initially at state 1. The system is initially at state 1 at a pressure P1, which is at a pressure P1, and let this pressure be equal to the external pressure P. So the gas, it exerts a pressure P1, whereas external pressure, let it be P. So the system, the gas is confined in piston cylinder assembly. It is at state 1. At state 1, let the pressure be P1. Pressure P1 is equal to external pressure. Okay. At this state, let the volume occupied by the gas, let it be V1. Let the volume occupied by the gas at state 1 is V1. Now, the system is undergoing a change of state from state 1 to state 2. How? The initial pressure that is applied on the surface of the piston is gradually reduced, or it is slowly reduced to a pressure P2. If the external pressure, if we remove this external pressure, if the external pressure is continuously and slowly reduced to a new pressure P2, to a reduced pressure P2, the piston will rise up and it will take up a new position. So I'll explain it in another figure, but it's happening in the same cylinder, piston cylinder assembly, same cylinder. The system at state 1 at P1 V1, it's now the pressure, initial pressure P1 is, external pressure is continuously and slowly reduced to a new pressure. So it will take up, the system expands, the gas expands, and it takes up a new state, let it be at state 2. The gas expands because the pressure exerted on the system is slowly reduced, so that it expands and the gas takes up a new volume which we call as V2. At state 2, let it be V2, and the pressure, let it be P2, which is equivalent to the external pressure at every given instant. Okay. So the system has undergone a change of state from state 1 to state 2, and initial state properties P1 V1 has varied to P2 V2. If the surface area of the piston, that is exposed to the gas, the surface area of the piston that is exposed to this gas is A, if the surface area of the piston that is exposed to the gas, if it is A, then the force acting on the piston, could be written as F is equal to, so if P is the external pressure which is equal to the system pressure or the system gas pressure, at any given instant during the expansion process, the external force acting on the piston is given by F is equal to P into A. Or the force acting on the piston can be written as F is equal to P into A. So the displacement of the piston, that is the displacement of the piston from an initial height Z1, to the new height Z2. So the displacement of the piston is related to change in volume. Displacement of the piston, which means actually there is a change, displacement of system boundary. System boundary is this. System boundary. So there is a change in system boundary. So the displacement of the boundary, system boundary. Okay. So the displacement of piston in the direction of force, is related to change in volume. Is related to change in volume dV of the gas. Initial volume at state 1 it is V1. Once it is undergone a transformation from state 1 to state 2, the volume has changed to V2, a larger volume. So this dV is related with the change in the displacement, that is dz. From Z1 it is raised to a new height Z2. The piston level has changed to a new height, that is Z2. So the change Z2 minus Z1, that is dz, is equal to dV divided by A. Right? dV is change in volume meter cube. The area of the piston that is exposed to the gas, piston surface exposed to the gas, that is meter square. So dz in meter. Okay. So the work done during this expansion process, work done is dW is equal to, according to the mathematical statement, dW is equal to F into dz. Okay. So the force acting on the piston can be replaced in terms of P into A multiplied by dz, which is equal to PA. dz can be replaced in terms of dV, so dV by A. So work done dW, differential amount of work done dW is equal to P into dV. So if the volume of a gas changes from an initial volume V1 to a final volume V2, then this equation 1 can be readily integrated in order to get the work done on the face of this piston. So work done W, can readily integrate the expression 1. Work done is equal to integral between the limits V1 to V2 PdV. Equation 2. So this pressure volume history of the gas undergoing the change of state can be represented on a PV diagram. It can be represented on a PV diagram, pressure volume diagram. PV diagram for reversible, PV diagram for reversible expansion of gas. By reversible, if the P external pressure P external, if it is equal to the system pressure, if it is equal to the, so the pressure volume history of the gas undergoing this change of state from state 1 to state 2 can be represented on a PV plot. So we are going to draw the PV diagram for reversible expansion of gas. Why it is reversible expansion of gas? Reversible means the external pressure should be equal to the gas pressure. External pressure is equal to the pressure exerted by the gas on the cylinder, on the surface of the on the inner boundary of the cylinder for all volume at every instant or for all volumes. Then in such case it expands slowly. It undergoes and it actually expanding slowly, which means it undergoes and there will be an infinitesimally small pressure gradient exists between the external as well as the at the external point on the surface of the piston and at the inner point on the inner surface of the piston. So at the external pressure P, once it is equal to the pressure exerted by the gas, there will be an infinitesimally small pressure gradient or close to the pressure of the system pressure or the pressure of the gas. Such processes are called as reversible process, which means it expands slowly, infinitesimally small, or reversible process means only an infinitesimal system changes occur over an infinitely long time. So it's a reversible expansion of gas. Now this integral that is given by the area under the curve between the limits V1 and V2. So we are discussing about the reversible expansion of gas. Initially the system has state 1. The state properties at state 1 was P1 V1. So it is at a higher pressure, then the pressure is reduced and it expands to a lower pressure P2 and higher volume V2. So initial state 1 you can represent as a higher pressure state 1 at a higher pressure and occupies a lower volume, that is V1. Okay, and once it undergoes a quasi-static expansion, a quasi-equilibrium process at each and every state, and once it undergoes a gradual expansion when the external pressure is released or when the external pressure is reduced slowly, you could see that the pressure has reduced to the pressure P2, it has reduced to pressure P2 to a lower pressure P2, higher pressure initial state P1 to another state. The system has moved to another state 2. It has moved to another state 2 where the pressure is low, whereas the gas occupies a larger volume, that is V2. And you can join at each and every instant. You will get many number of points. You can join it in order to form a smooth curve, and the area under the curve, it represents the work done during the reversible expansion of the gas. So this area under the PV plot, it represents the work done between the limits V1 to V2 PdV during the reversible expansion of the gas. So the area and hence the work done in the compression or expansion of the gas, it depends on the shape of the PV curve. It depends on shape of the PV curve. If it is an expansion process, it takes up a new path. It takes up a new path in the expansion. It takes up a new path. Say this is path A, whereas this is path B. So during the compression process, we need more energy in order to compress. We need more energy to compress the piston to new state, piston to an initial state, and we need more amount of work done. So the area under the curve, according to curve A and curve B, it differs. So the work done, it proves that this is establishing a fact that work done in a process is a path function. Work done in a process is a path function.